Okay, we got a couple minutes. Let me just start by showing this video. If you remember a couple classes ago, we talked about what happens if you remove an atom from the middle and move it to the surface, that it's going to start to grow, but it's not going to just go anywhere on the surface. It's going to find where there's an edge already formed and then keep growing. And you can see that here. So this is an image. We'll talk about how they made this image in just a moment. But you can see they take a bunch of still images and put them together to make a video. And see like these sheets of materials, they grow because atoms sit on the ledges and that just grows outward. And if you leave this, it's slowly coarsening and growing over time, right? So films grow like this. If you do what's called physical vapor deposition spudding, let's show that one more time. Right? If you grow these things by just bombarding a surface with atoms, they could sit just anywhere. They could just sort of speckle it like spray paint would. But if you do it by giving it a little bit of slow time and then giving it energy, do it slowly so it has lots of time, it's going to grow specifically by going on those ledges, which makes them a nicer, more uniform film. Okay? So there's that for today. So how did they collect that image, right? Those were actual atoms you saw, right, growing along there. So how did they collect that image? What do you guys think? Taylor. Oh, yeah. Eventually it would. And you notice it actually was kind of the direction it was going. If you look at how it was in the beginning, it had some deep canyon sort of thing. Those slowly are getting filled in. By the time you're done, it's starting to look a little bit smoother, right? And if you gave it, basically, there's a competition. You're bombarding it with atoms, so that's adding more atoms. But then it takes time for them to find the lowest energy position, and they have to be able to diffuse and move around to find that lowest energy position. So it's a competition between adding too much and not giving enough time for them to move around. If you do this really slowly, meaning your flux of atoms to the surface is low, and you give it plenty of energy for them to move around, it'll give a more homogeneous, nicer surface. But at the cost of growing very, very slowly. So it's a trade-off you have. So how do we make this image, right? They say STM. What's STM? It stands for, anybody heard this one? It stands for Scanning Tunneling Microscope. So it's a type of electron microscope. You could also make this with AFM. And that was the last thing that we didn't get to last time, so let's briefly talk about AFM. So you don't need to know the details of these different microscopes. It's enough to know that, here's a good question. This would be something that I could ask you on. Why are you able to achieve a higher resolution with an electron microscope as opposed to an optical microscope? That's about the extent I expect you to know. So turn to your neighbor and take a stab. Why can we get higher resolution with an electron microscope as opposed to an optical microscope? Okay, what do you guys think? Let me pick on Tyler in the white shirt in the back. That may not be your name. I think it's Tyler. But you don't know the answer. Phone a friend. All right, next to him. What's your name? Anthony. What do you think? Why can we get better resolution with an electron microscope instead of an optical?
I'm guessing that because the electron microscope can see things that are actually smaller and your eye doesn't have to process it.
Okay, that's a good point. You basically said your eye wouldn't be able to process it. That's not actually terribly off from the right answer. The answer to this is that the wavelength of light that you hit the sample with is way, way too small, right? If we use something like an electron microscope, if you let that hit your eye, it would actually damage your eye, and it certainly wouldn't be turned into an image, because our eyes can only turn things into image, light that's between, what I think we said like 300 and 700 roughly, right? We can't see outside of that wavelength window. But an electron microscope doesn't have that problem. It can convert any wavelength into a signal, right? So you're actually not terribly far off on that. Now, why can we go to smaller resolution? Is because if you use, imagine wavelength of light, 300 micron or nanometers. How are you ever going to see something smaller than 300 nanometers, which like atoms are? You can't. You have to move to a light of a wavelength small, at least as small as the atoms, which an electron microscope can do. So we talked about scanning electron microscopes. We talked about transmission electron microscopes. Basically, one, the beam of electrons bombards through the sample, and one hits the sample and bounces back, right? And you can make cool images. The very last thing we said was EDS, Elemental Analysis, where basically you can not only capture an image, which the one on this left, right here, oh, sorry, let me give it a color. This one, you can barely see like two different colors there, but it's not very clear. And then when we move that to backscatter, you can distinctly see two different phases because the contrast is proportional to the density of your sample. And all of a sudden you've got two different density pieces that you're looking at. And then we did even better when we added elemental information. And that's where we left off last time. So there's one more thing which we should talk about, which is scanning probe microscopy. One of them, the most common one, is AFM, which is atomic force microscopy. And how this works is actually pretty clever. Atomic force microscopy, or AFM, works by taking a tiny little tip, right? And they get these, try and get them like atomically sharp, right? And they put it on a cantilever beam, so this thing can rotate up and down, and they tap along a surface, right? So if I'm a machine and I've got this little cantilever, I'm going tap, 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 it's looking flat, and then I hit something slightly higher. I say a little bit higher, tap, tap, a little bit lower, right? So it's only a surface measurement. This will only give you information at the surface. It doesn't probe underneath it, but it can produce very nice topological images of the surface, or topographical images of the surface, right? And some of these are actually incredibly sensitive to the point where you can visualize atoms, which is amazing. Like literally this funky organic molecule, they were able to sort of hold it in place. I don't know how they did that. Probably just cooled it down so this thing couldn't reptate, which is when a polymer sort of rotates a little bit, or diffuse around the surface, and then they tapped it, and they were able to produce an image of the structure, which is pretty stinking amazing. So I think that's what they did here. They used a scanning tunneling microscope, which is, it's using a similar technique to visualize a surface. It's not tapping it. I think it's actually using, ASTM I think stands for tunneling. In that case, what it does is it brings this surface, it brings some sort of probe near the surface, and if you apply a voltage across here, as a function of how far away from the surface you are, you can actually get electrons to trickle across to it, right? They tunnel across the energy barrier. I'm pretty sure that's how it's doing it. But it's the same principle. It's measuring the surface. And if you take a bunch of those images and then splice them together over time, you can create images like this one where now all of a sudden you can see films growing based on how atoms would be moving and choosing where to sit. Okay? Okay, that's chapter 5. We're going to skip chapter 6 and come back to it in a couple. Let's go to chapter 7, which is mechanical properties. So our objectives for today, what do we want to learn? We're going to review basic stress and strain, which you guys should have seen in high school, I'm guessing. Certain mechanical engineers in your intro course you saw it. So we'll be brief on that. We'll talk about Hooke's law, which again, most of you will have seen. You've all taken physics, so you would have seen Hooke's law. We'll identify yield stress, the proportional limit and ultimate stress. We'll talk about strength, toughness, resilience, and how we get these from stress versus strain curves. And I think we'll have time to get to Poisson's ratio and by the end, okay? So we've talked about solids, we've talked about defects in solids, and we left off last time saying some things like, remember sterling silver. When you put a little bit of copper in with your silver, we made it stronger, right? And we just started to explain that. So before we can get into the mechanisms of how things get stronger and tougher, we need to talk about what is strength, what is toughness, right? Why do mechanical properties matter? Well, forces are applied to all the materials around us all the time. Every one of you is sitting in a desk where some engineer somewhere had to figure out how thick does this aluminum have to be or steel have to be, or is this going to deform? Is it going to deform too much? They had to do these calculations because it's all around us, right? A lot of the things that break that lead to accidents or safety concerns have to do with mechanical forces causing an object to fracture. Not always, but oftentimes. And maybe your material has a deformation that's supposed to happen. Maybe that's its critical function, right? A pole vault. You know, a pole vaulter, when he uses pole vault, whatever you call that, the pole for pole vaulting, right? That thing is supposed to deform in a certain way. They design it to deform in a certain way, and many applications might have that, right? Skis, I mean, half the stuff that we design they're meant to have a certain amount of deformation. So we need to understand how deformation works in material in response to applied loads. So in this chapter, we'll be able to answer questions like how strong is the material, how much can it deform, is that deformation reversible, or am I permanently deforming it? Okay, and we'll talk about it in terms of classes of material. So if we're going to be testing materials for strength and deformation, one of the first things we need to get to is how do we make sure that we're all doing it the same way, right? If I send a sample to Andrew and I send a sample to Tyler and I say, tell me the ductility of the sample, I have to give them a means whereby they can both test that the same way, because ductility is a kind of a nebulous term. They're like, well, I can flex it a little bit, and what do they come back telling me, right? So there needs to be ways where everyone can test it the same way and test it same way such that you get the same answer, whether it's done in China or United States or wherever else, right? So for that, there are actually whole organizations that dedicate themselves to trying to answer this question of how do we test things and have a uniform way that everyone agrees on this material is such and such strength, right? And so the American Society of Testing Materials, ASTM, is one way. ASTM International, they put out what are called standards, which are a set of procedures, slowest internet ever, a set of procedures for testing pretty much anything you can imagine. If there's a product out there that has a property of interest, there's probably an ASTM standard for measuring that property. That might be how long it takes for cement to set up and cure. There's definitely those. That might be strength under tensile loading. It might be all sorts of things. And some of them get pretty specific. Like here's one that we had to do recently. A company, since I run the characterization lab at the U, they asked us to figure out how well does their lining material stick to the substrate underneath it, right? It's think of it like a composite. There's a steel substrate, there's this polymer that's on top of it, and they have to like peel this thing off. This is not our video, this is someone else's, but this is the test we did. And they said, we need you to do ASTM D1781, right? And we said, all right, what is that? We looked it up, and it's called a climbing drum test. How it works is you clamp the sample up here, you can see it just barely. It's got a steel substrate probably. It's got some sort of lining on top of it. You clamp onto the bottom, and then the lining itself is connected to this rotating drum, which causes it to slowly peel. You can see it. It's a short video. As they run this experiment, you'll see it, that drum slowly climbs apart. You're basically peeling this thing off. So the diameter of this drum, the rate at which you do it, the force that you can apply, all of that is prescribed, and you measure the pounds per linear inch of this to get delaminated, right? And since this is an ASTM standard, it doesn't matter if I do it here or in New York or wherever, they can say, hey, our product complies with ASTM, D1781, and it has such and such a delamination strength, right? So some of these are strange, right? They're out there, but it's necessary that we have them because otherwise it would be totally subjective. A group could say, hey, we have this super strong material, but that's only because they measured it in such a way that it exaggerated the strength. So we all need to have something that allows for even comparison. Okay, let's talk about types of loads and forces. This is stuff you would have seen before. There's different types of loads that you can apply to a material, right? There's tensile. So imagine that we initially had a material with this dotted sort of profile, right? So that sort of ghost shape there. After you apply a load, this is pulling it apart by taking the force and loading it perpendicular to the face. We get this final shape with now the not broken lines, the solid lines. So it's stretched out and it got a little bit skinnier, right? If you apply a load in compression, we now call this a negative force, just by convention. We call negative forces compression, right? And its initial shape was here, but its final shape is now shorter and sort of squattier, right? You can do shear. Shear is now when you apply a force, but it's no longer perpendicular to the face, it's parallel. So when I push on this table, right, when I'm leaning on it, part of my force is still pushing down, right, because I'm not like glued to the table. So there's a component of regular compression, and there's a component of shear, where I'm actually shearing this table. The floor is holding it, so there's an equal and opposite force. I'm pushing it this way, the floor is holding it with an equal and opposite force that way, but the table technically is deforming a tiny bit. It's just not much that we can see it, right? Some things are very compliant in terms of shear, and you could squish it and see like a major change, like rubbers. You can see those things change quite a bit, right? And then torsion is just a special type of shear that produces rotation about a longitudinal axis. So we'll talk about these each in turn. First up, tension. Tension is almost always done under uniaxial conditions. It doesn't make sense for me if this is the thing I'm testing. I usually would pull it like this. I would pull it like this and have like another wire trying to pull at some funky angle. That wouldn't make sense. We're generally talking about uniaxial tensile tests, right? By the way, if this is anybody's, who's here, right? And they often have a pre-described shape, which is called in the industry a dog bone, right? Looks kind of like a dog bone. If you look at the ASTM standards for any sort of tensile strength, it will say exactly what shape and size and conditions it's allowable to have for your samples, right? It'll even say like, what is the radius of curvature on these like curved in sections? What is the, it's very, very detailed. Why does it have to be narrowed in like that? Let me pick on one of my MSE students since I know you did this yesterday. Daniel, let me pick on you.
It has to be like that because when you load it in the machine, you have to have something to grab onto like this so that it like narrows down the force doing that so that it's pulling across the part you want to test all the time.
Yeah, like this is the dog bone. When you grab onto it, you're using something kind of like vice grips, which have like a bunch of little tiny teeth and you clamp onto it. So you actually can see after you test this, it has like a bunch of little lines like that from like the vice grips clamping onto it. If this is at all of a brittle material, that's just a complete non-starter. You can't vice grip onto your dinner plate at home. It would just break, right? So ceramics they just don't work for this. But polymers and metals, you can do it. However, you're gonna have some stress that's amplified local to that little thing. So to avoid it from breaking right there and therefore not giving you a real feel for the strength of the material since it's now an effect of the loading, we actually want to narrow it, right? So this has some cross-sectional area up here. This is going to have some smaller cross-sectional area in that part, right? The point being that if you go down in cross-sectional area, what do we do in terms of stress? We go up, right? Because stress is equal to the force divided by the area. So if you go down an area, we magnify the stress in that middle region, which causes it to fail, somewhere in the middle, where we wanted it to, rather than where it's being gripped onto, which we don't want. So they'll be either clamp on or sometimes screw in dog bones where you can screw them in. But that's a standard shape that you'll do if you want to test your material. So if you guys end up working for Wheeler or Caterpillar or Kennecott and you guys need to talk about the strength of your materials, you'll have to send your materials out to be machined first and then tested according to some ASTM. So stress is a force, but it's not just a force, it's a force divided by an area, right? Force over area is stress, and then we have to have strain, epsilon. Epsilon is our strain. Think of that as the change in length, so L final minus L initial, the initial, or the instantaneous minus the initial over the initial, right? L final minus L initial over L initial, change in length over L naught, right? That's what's called engineering stress or engineering strain because we don't take into account real-time conditions, right? We're just saying, what were the initial conditions, right? If you had a rod and its initial cross-sectional area was known, you apply a load to it, that's its engineering stress. That's different than the instantaneous stress, which we'll get to in a minute, right? A few things here, that force is always in newtons, if we're not barbarians, and area is going to give me a meter squared. So Newton per meter squared, that is a Pascal, right? So you'll see PSI for barbarians among us that do pounds per square inch. It's not a very useful thing because a pound is not a force. A pound is a unit of mass that you then have to apply gravity to. It's just a terrible unit. It's a terrible, no good unit, but it's sometimes used. So use Pascals, right? And a Newton per meter squared is a Pascal. And 1,000,000 of those is a megapascal, right? Strain has no units, right? If you go back to strain, it was just change in length, so like 1 centimeter minus half a centimeter is still units of centimeters, divided by our initial length, centimeter. Centimeters cancel out, so there's no units. So sometimes it's given as a percent or as a parts per million, but it should have no units, right? Now there's compression test. We said before that force, if it's pressing down on a material, we call that a negative force. These are less common. They're still useful for a lot of things. They're just less common. There's shear and torsional tests. The big thing to remember here is that the force is now applied parallel to the face rather than perpendicular. Yeah, Callie?
Is a tensile strength the same as the compressive strength?
Sorry, one more time?
Is the tensile strength material the same as the compressive strength? Is that what you can use?
No, they're not. It's just that it's more commonly reported. It's easier to do, I think. Well, actually, compression would be easier. But more commonly, yield strength is as a function of tensile loading. For ceramics, that could be wildly different than its compressive strength. Their compressive strength is about 10 to 15 times higher than tension, right? For a lot of materials, they just don't report compression, they report tension. I know, but they're not the same thing. Definitely not the same thing. If you have a material that's being sheared, right, it started out like that, and after you shear it, it's now deflected at some angle. Say that angle there. If you take the tangent of that angle, that's gamma. That's our shear angle, right? And then in the real world, there's not just one load. There's actually, it can be combinations of load. And one way to see that is imagine you had a cylinder to start with that wasn't broken in half. This was together. If you apply a load to it directly perpendicular to that face, right? It's perpendicular. Then you think that you're applying pure tensile load to this, and you are. However, we could imagine that somewhere within this material, along this plane, which is tilted by some degree theta, that on that plane, you now have both tension, right? We'll call that the, that's a terrible color, sorry. You have tension, you have a resolved tension on that plane, and you have a resolved shear on that plane, right? So resolved tension and resolved shear is as a function of whatever plane you're talking about, okay? So we have formulas for those, right? The tensile stress in that plane could be given here if you knew the angle, and the shear could be given through that angle. We're going to come back to that in a minute because a lot of materials, that becomes important because the atoms slide past each other along certain planes. Remember we did Miller indices and we figured out planes in a crystal? They slide past some, but maybe not past another. So we need to figure out the angles and calculate the resolved stresses. So we'll come back to that next chapter. Sorry, chemistry never goes away, right? Okay, there's elastic deformation. When you guys took chemistry, or physics actually, you probably saw the example where they took a spring, right, and they put a mass on it and they started it oscillating. And they talked about, the different mass or the different spring constant can change the rate of oscillation and the amount of deformation, the deflection of the spring, right? So that is just a manifestation of Hooke's law. Hooke's law says when you apply a stress, right, sigma, you're going to get a strain. And how much strain you get is just proportional to the constant of proportionality, which in this case is Young's modulus, sometimes called the elastic modulus or modulus of elasticity. Those are all the same thing. Young's modulus, modulus of elasticity, all the same thing. And since strain is unitless, this must have the units of stress, so it has just megapascals, or more commonly gigapascals because it's much larger, right? If a material is proportional, then we call it elastic deformation. And this means that it's non-permanent and it's reversible. So I take a rubber band and I stretch it. The amount of stretch that I get for a given load would be the Young's modulus. And since it goes all the way back to how it started after I take the load off, we call that elastic deformation, like an elastic band. It's elastic, it goes back, it's not permanent. There is a point on an elastic band, if you pull it too much, it's now permanently stretched out. It'll be a little bit more stretched than when you started, or it'll even break, right? That's plastic deformation, meaning permanent, right? So our first clicker question for the day, when we plot stress versus strain, think of our equation here. Stress equals the constant of proportionality times strain. Some materials are going to be more compliant. They're going to give a higher amount of deformation, right? And some will be lower. So which one of these are which? Let's start with the first one. Which material on this plot, pause it while you log in, which material is the ceramic? Is it the blue, red, green, or purple line? For those that may be colorblind, that's purple, green, red, blue. Purple, green, red, blue. I'll write that. Purple, green. Okay, so which one is the ceramic? When you apply a load, think of what happens. Should it stretch a lot or a little? Okay, people think red. Oh no, blue. Okay, I saw the red color. I was like, what? Sorry, my brain. Good. Most people think blue. How did you know? Somebody who got it right. Tell me what you thought. Pick on somebody who got it right. Anybody? Rachel.
So we know that the ceramic isn't going to deform once it gets past that elastic deformation. So there's not going to be any sort of curve.
Yeah, this one's got that little like hook. It technically does start to plastically deform, which we'll get to in a minute.
Since there's no plastic deformation with ceramics, and it has
Can rule that out. And basically, when you apply a huge stress, you don't get very much strain. If you take a dinner plate, you can pull on it pretty hard. It won't actually break at very low loads. The ceramics can be strong, they just aren't necessarily compliant at all. They can't deform very much, right? They're not ductile at all, but they can be fairly strong, okay? So our next one then, which one's the polymer? Okay, people think that it is D, mostly. A quarter of us think green, but mostly D. Okay, good. And then I think there's one more here. Oh no, hold that thought. We'll come back to that one. Okay. All right. So, which one would be a brittle steel versus a ductile steel? Red is what? That would be our brittle steel because it can't deform very much before it breaks. It might be stronger, right? But this would be our ductile steel, right? Because even after the point where it's no longer proportional, look, it just goes quite a bit more strain before it finally breaks, okay? You can technically have nonlinear elastic deformation, meaning you pull on it and it's going to go back to normal, but it maybe gets easier and easier the more you pull, or even harder and harder the more you pull. But it will go back, right? So rubber does this, cement does that, some polymers will do that. Meaning you could stretch it out to this point, but it might still go all the way back. It just depends, right? If it's elastic, the key thing to remember is that it's reversible. There's no permanent deformation. Let's get that. So I think we've talked quite a bit about forces and interatomic distances this class, but let's do it one more time. We said that if you've got some interatomic distance R here, and you have a net force is 0, that corresponds to R naught, right? R naught is when there's no net force, so force is low here, and then it comes up and comes down. We said that the modulus is just, that's a really bad line. Let me fix that. I don't approve of that line. Right? This is better. At that point, the slope of that line, right? Remember, this is force against separation, distance, right? So the slope of this line means the higher the slope of that line means the more force you have to apply to get a very small change, right? So that's a stiffer material. That's like a ceramic, right? And if it's a polymer, then it's something that would be way lower slope because the same force would produce much more change in the x-axis. So what are some typical values that you should know for materials? Ceramics are higher than metals or higher than polymers in terms of their elastic modulus, right? Ceramics can be gigapascals, right? Some of them like 400 gigapascals, maybe 50 to 400 is okay regions. Remember, gigapascal is a billion pascals now, 10 to the 9th. But polymers could be, less than a gigapascal. They could be 0.1. And metals are going to be somewhere in between, okay? Modulus decreases with temperature, generally speaking. Some rubbers don't do that. They stiffen as you heat it up. But most materials, you heat it up, and it becomes more compliant. You should probably have experience of that. Most things, you probably experience that in real life. You heat it up, it's a little bit more compliant. Now, just like that was with shear, with tensile load, and you got a modulus for tensile modulus, you can get the same thing for shear. Eric, question?
Just kind of a concept question. If you have a material that gets stiffer when you heat it up, does that mean it will burn rather than melt?
That's a very good indicator of it. I don't know if that's 100% of the time, but that's a very good indicator of it. Because it probably means as you're heating it up that your cross-linking process is continuing. It's using that thermal energy to further cross-link or maybe thermally cross-link. And therefore, if it's cross-linked, it's not going to melt. So it's a very good indicator because as cross-linking goes up, it's getting stiffer. So it's a good indicator. There's probably exceptions to that rule, though. Okay, just like for elastic modulus under a tensile load or a compressive load, you also have it under shear conditions, right? If you shear something, you're going to end up that the shear stress will produce a shear angle proportional to the shear modulus, right? So shear modulus is something that you can calculate just like the other one. There's anelasticity. Anelasticity means that instead of getting an immediate elastic response, there's a time-dependent nature. We're going to come back to this because it becomes really important. It typically means that there's some sort of microscopic or atomic process that's happening that takes time, right? Polymers are a great example of this. Imagine your climbing rope, if anybody goes rock climbing, you've got a big tangle of rope, right? If you want to pull that thing, the coils have to sort of align themselves for it to stretch it out, right? It's taking time for these coils to align. Same thing in polymers. If you stretch something that's polymeric, and this is, it's cotton, so it's polymer of some sort. If I pull on it, it would have some sort of time response in terms of I apply a load and it doesn't instantaneously change. It's slowly going to change in response. And some things are really dramatic, like I think silly putty we were talking about. Some of them change really dramatically and some not so much. We'll come back to that. Okay, there's Poisson's ratio. Poisson's ratio says that as you pull on something or push on something, sure, you get a change in terms of the strain in the direction that you're pulling or pushing it, but you also get change in the dimensions transverse to that. What do I mean? So if you're pulling something, we know that an object, if I pull on this, it's technically stretching out a little bit. That's obvious. Poisson's ratio says it's also, Carl says, right? So it's contracting, right? And alternately, if you push on something, it's technically getting a little bit wider, right? So we need a way to quantify that in case it becomes significant. In a lot of cases, it is significant. So they defined Poisson's ratio. They said it's negative because they wanted to have a positive value. Positive, if you're loading it in the z direction, so up and down, then you take the strain in either the x or the y direction and divide it by the strain in the z direction, which might be stretching, right? So under tension, you should get a positive value for Poisson's ratio, right? What are values typically? Somewhere between maybe 1/4 and 1/2, right? That's typical, and for a lot of metals, it might be between 0.25 and even 0.35. Some things are really far out there. Cork, for example, is the example I usually give. Cork has a Poisson's ratio of, let me get this right, it's 0. Why does Poisson's ratio equal 0 for cork? And then alternately, Poisson's ratio for rubber is 0.5. It's the maximum value. So why? What's going on there? Anybody have a guess why cork versus rubber? Yeah, Matt?
If you put any sort of force on it, it'll break.
It would. If you pull it apart, it breaks easy. Let's talk about compression. If I compress cork, if it has a Poisson's ratio of 0, that means as I squish it down, it's not getting any fatter. Why? Its density can increase. Cork is not a fully dense material. It has tons of pores in it, right? It naturally grows that way. It's got tons of pores. So as you squish it, you're just compacting those. So it technically is getting wider. It's kind of a trick question, right? It's getting wider because its density can change. It's filling in those voids. If you had a cork somehow that didn't have those voids in it, it wouldn't be cork anymore, but it would now expand, right? Now rubber is the other extreme. As you apply something, it's so compliant, it's so easy for it to deform that it just expands very, very, the maximum of any known material out, basically, 0.5, okay? If you have these values, right, if you have Young's modulus and shear modulus and Poisson's ratio, there are expressions like this one that can relate them. So this is a super common test question, homework question. I'll give you information to solve 2 of these, and then I'll ask you about something relating to the third. Right? I'll give you a plot for Poisson. Maybe I'll give you a plot for like stress versus strain. The slope of that would give you Young's modulus, right? And then I say the final dimension was this when you applied a load of that, so that allows you to figure out Poisson's ratio, because I told you how much it contracted. And then I might ask you what a shear angle might be if it was loaded under some shear stress. So you have to figure out what G is from these 2, and then solve for a shear angle. Yeah?
Poisson's ratio doesn't have to be the same in the x and the y, right?
So we are talking about isotropic materials. I think I mentioned that right here. Yeah, if a material is isotropic, then we say that strain in the x direction and y direction is going to be equal to one another. If you have anisotropic materials, it throws it off, and we're not going to cover that in this class. In your mechanics classes, you will see it, not in this class. Any questions on this equation, on anything we've covered so far? Seeing some sleepy eyes. Let's shake it up. Let's do something different, right? Okay. How do we know when a material is yielding? What is yield? First off, what is yield? Turn to your neighbor. What does yield mean with material science? Hint, it's right around 0.3. Okay, how do we know when a material is yielding? Let me pick on Kara. I think it's Kara.
stretched to the point, like if it breaks, or like it's stretched to the point where it's go bad.
Good guess. You're guessing then that the definition of yield has something to do when the thing breaks. That's a good guess. It's not right. It's a good guess though. Anybody have another thought? In the red. Yeah, it's when plastic deformation begins. And that's a super hard thing to do because if you look at this plot, that's about at 0.3, right? Here's our Young's modulus, meaning you apply a load and you get some sort of strain. And technically, the very instant when it starts to have permanent deformation, that's when you have yield, the onset of yield. In reality, that's super hard to measure because it's going to be really, really small. So you'd have to have really, really sensitive equipment on there, right? So instead, we as a community, we've gotten together, we said, how do we talk about yield of materials? We've said, well, let's just pick a point where everyone can easily measure. And that is when you pull it, and then when you let go, when it goes back, and there's a leftover strain equal to 0.2%, that is our yield strength. Just by definition, totally arbitrary, right? But that's what we've decided on. What that means is that if you load this up 1 to 2, and then you let go, it'll go right back to 0. It'll have no leftover strain, totally elastic, right? If you load it to 3, anywhere beyond 3, technically, if you unload it, it will go back with the same slope as its Young modulus, and you'll have some leftover strain, right? That's plastic strain that you've left in your material. So we just as a community, we said, all right, as soon as it gets to a point, which is 4, where the leftover strain is equal to 0.2%, we'll call that our our yield strength, right? So yield strength, sigma y is what that's usually written as. Questions on that? Yeah, run your name. Katie.
Is it 0.2 just because it was hard to measure 0.1 or less?
No idea. I have no idea the history of the 0.2. That is what it is. I think it's probably fairly easy to measure. I don't know the history behind that, but that is what it is. So when you look up on your spec sheet for your steels or your coppers or whatever you're using and you see yield strength, technically it is yielding a little bit at the value that you've taken it to. It's just a small amount of permanent. Yeah, Kylie?
I have 2 questions. First off, like, if you have 0.1% where it can be significant at all, is that kind of...
If you have what percent?
Like, if it went back and you had 0.1% strain or whatever, is that just kind of insignificant?
It just depends on the application.
Okay.
Depends on the application, right? If it's a piston in your car, what's the tolerance of the piston inside of the cylinder? Pretty small, right? Would 0.1% make a difference? Maybe. I don't know. Just depends on the application.
It's like 0.1% overall.
Oh, absolutely. Yeah, if it's that's absolutely true. If you keep on loading this is going to keep on adding up. That's actually true. We'll talk about that in a minute. What happens when you unload something and then reload it again? We're getting to that in just a minute. The thing to remember here that I want you to remember is that when you let this go, let's say we loaded it up to here, and this corresponded to like, I don't know, 0.6% strain. When I take that stress off, you're not left with 0.6% strain, you're left with 0.2 because it's going to go back by whatever its modulus was, right? Question?
Yeah, how does time play into this? Like, if you loaded it to a point between, or like F4 or whatever, for a day or like for a year, would it go back to the same?
Great question. If you have a material that is anelastic, right? If we go back up here, we said anelasticity means time dependent. Then you have to then these should be equilibrium, right? You should let it sit for infinite amount of time, right? Most materials aren't strongly anelastic. Metals, for example, at some temperatures they might start to become anelastic, right? But yeah, technically, just like phase diagrams are under thermodynamic equilibrium conditions, technically, yeah, this thing, if it's still changing, you should leave it there. Right? That make sense? No? So some materials, if you load it up to something and you unload it right away, you might see no permanent deformation. But if you let this thing sit for a good long time, those polymer chains maybe might slide past each other to the point where now when you take it off, it just stays put. What do we call that? There's a term for that. We learned about it earlier. We called it plastic deformation that's not there instantaneously, but over time it is there. We called that creep. That's creep. So you're talking about creep. So to solve this, like these plots don't take into account creep. You'd have to have a more sophisticated stress versus strain plot to account for creep, right?
So is this saying the maximum, like if you left it for infinite time and then released it, it would go to, like this is what you would end up with?
For this material, however long they left it there, when they took it off, it had 0.2% left over.
Okay.
So when you report these, yield stress has to be as a function of conditions, right? So that's why there's ASTMs. It would tell you how long you hold it for, how many times you have to do this maybe, what temperature this happens at. That's why ASTM standards have to exist, because there's all these other variables that could give you, unfortunately, incorrect values. Or just confusing, like multiple values for the same thing. But there's not actually multiple phenomena happening. Or sorry, there's not multiple values, there's multiple phenomena happening. There's just different things. Creep or no creep, basically. Any questions else on this? Those are great questions. Okay, let's keep going. Okay, further than I thought we'd get. So we have more learning objectives. All right. So let's talk about ultimate tensile strength. We'll come back to this next time maybe. So when it does start to yield, it might be nice and gradual, right? It might be like this, where it just slowly bends over. Or you could have something really funky happen. It could like do this and then go back up, right? So that's what's happening here. They call this yield point phenomenon, where basically you're pulling on something, it's looking totally elastic, and all of a sudden the load might drop in it. You might see a sudden increase in the strain, right? It might do something here, and then it'll pick up at a more normal rate. That's actually a really common thing to have happen when it starts to yield. At the onset of plastic deformation, it can do something a bit funny here, okay? Yeah?
Is that going to happen with our wire on the weight, that one experiment we did where it went down, went back up and down, up again?
No, good question though. That one was interesting. Remember on the wire we had that we heated up, right? That thing went down because we were heating it up, and at a certain temperature went from BCC iron to FCC iron, which is a more compact structure, right? Higher atomic packing fraction. So if it compacted, the wire had to contract. So it actually went up, and then when it kept on heating, it kept on expanding. And then in reverse it happened. So that had to do with a phase change, not to do with a yield phenomenon. Good question though. So what are some typical values for yield strength? Just two that you ought to have in your back pocket when you think about engineering materials is that aluminum is about 35 megapascals. That's not very high. Aluminum bends pretty easy, right? The point at which you bend it and it's permanently bent, 35 megapascals. It's not very high. Steel is an order of magnitude almost 2 higher than that, 1400 megapascals. Yeah, question?
Kind of related to that previous question, is it possible for stress to cause a phase change?
Oh, absolutely. Absolutely. There's whole fields dedicated to that in material science where they'll put things in what are called diamond anvil presses, where it's like it's a press that applies just ginormous pressures on something, and then they'll try and look at what phase is present using complicated diffraction, and they show that you can change phases by just applying stresses.
So in that sense, it kind of would be similar to the...
Yeah, in that case it would be. The one that we talked about is just a thermodynamically favorable change in structure, which corresponds to a change in stress. Or, a change in length, because it has a different packing ratio. But you could force it to happen in some materials, and that's definitely studied. So these are some typical values you should have. Okay, the next thing is what Kara was talking about. Kara said, well, you're going to pull and it's going to break at some point, right? It's going to fail. That is now the tensile strength, right? Tensile strength, or TS. Sometimes they'll call it ultimate tensile strength, UTS, right? But this is basically the maximum stress that you can apply something, even if you don't care if plastic deformation is happening, there's still... right? This point is definitely permanently deformed at that point. Tons of permanent deformation. Doesn't matter. This is the maximum stress you ever reach, right? So that is our tensile stress, right? After that point, and you guys probably have experience with this, once you're pulling on something, you get what's called necking occurring here. It starts to stretch maybe, but it's getting easier and easier to pull until it finally breaks, right? So this region is necking at the end. So the next... did we pass the quick question? Oh, no, it's right here. Good. Where is it? Oh, I've lost it. Okay, right here. The question is the material... So the material seems to be getting harder and stronger up until tensile stress, right? Up here it's getting stronger and stronger, we think, because to stretch it, you have to keep on adding more and more stress, right? The question is it true that it's getting harder and harder and stronger up to TS and then begins to get weaker? True or false? Does it begin to get weaker after tensile stress? So, what do you think? True or false? Yeah. Okay, Eric had a good question. we're in this question, we're ignoring this yield point phenomenon, this little bit where it got weaker. Ignore that. We're talking about, the question is, right here, stress seems to be going up, harder, stronger material, but here it seems to be going down. Is that a true statement, that it's getting weaker? That's all. True or false? Okay. Phone a friend, get your answers in. It's amazing. I can, let me make it, somebody shoot me an email, like, Danny, can you send me an email and say give points for either answer on this one? I'll change it after class. Right now, only one of these is right, but I can change it. I'm surprised, very split. So, somebody argue one way and somebody argue the other. Andrew, which one did you think?
I chose true.
Okay, you chose true. You thought it's getting weaker. What was your argument?
Was the material, as you pull on the material, they may seem harder, and harder and harder until it actually pulls apart and weakens the point of porosity.
Okay, so you think that as you're pulling it apart, it's just getting weaker, and we can see evidence of that. I mean, this thing is going down. Oh, I've lost it. Odd. All right, I've lost it. Anyways, it seems to be going down, right? So, what's actually happening? Who wants to think the other way? Martine, what do you think?
I think it's taken relative to its original diameter. Once it starts necking, the actual true stress is greater, but there's still getting higher. But
Yeah, it's absolutely right. So that's the right answer. I'll wake up my pen real quick. So, what is necking? Necking is when you're pulling on something and all of a sudden the gauge starts to decrease. I think I've got a picture right here. Right here, right? Necking is not what you're thinking of, those who are giggling. Necking is this, right? You start to stretch it, and so like this distance from here to here is getting longer at first. That's just elongation. But after the tensile stress, the ultimate tensile stress, all of a sudden you get a region where something funny is going on. This thing bends in. It forms little necks, right? So that's necking, where you have a region of extreme local plastic deformation. There's general plastic deformation all over in this thing, but you get a region where locally it's doing something even more severe. So this cross-sectional area is smaller than we started. Therefore, if it got smaller, the actual stress is actually quite larger there. So these plots, these are engineering strain plots, right? This is engineering stress and engineering strain, meaning it takes into account just what the initial cross-sectional area was. In reality, that thing got smaller. If you were to account for that, it would look like the following. Do I have that plotted? It would look like this. So here's our regular plot. It went like this, right? If you counted for the real or the true engineering stress, engineering stress is the original, true stress and true strain would look like this. Meaning it is actually getting stronger and stronger because of something called cold working, which we'll get to later. Like the more plastic deformation, the harder something gets. It's just that it looks like it's getting weaker because it's necking down, right? So if you were able to plot the instantaneous cross-sectional area, which means you'd have to have some sort of thing to measure that area constantly, even when it's necking down, the plot would look like the red one, okay? So that is false. Because it doesn't take into account the change in the instantaneous cross-sectional area. And I'll give credit for either one on that. Kylie?
I'm a little confused. Like, it makes sense conceptually, but at the same time, when it necks, the area gets smaller, but the force is the same.
Yeah, but stress, yeah, you're absolutely right. The force is the same maybe, but stress equals force over area. So if this goes down and that stays the same, that goes up.
But then why does it go down on the graph?
It goes down on the graph because
Like, what's getting measured that causes it actually,
it's basically saying that the perceived stress is going down, right? Is what you're actually perceiving there. Does this make sense? Like literally, like the stress that you're applying to something based off of your initial calculation, it's just going down. So it's taking less and less force. So force is what's changing actually here. Right? If you pull on something, it seems like you don't have to pull it as far. When it's at the very end, like imagine like silly putty, right? Taffy. I should bring taffy for this, right? You got taffy, you're pulling on it. After it starts necking down, you don't have to pull as hard. It's like finishing up, right? So you're applying less force, but stress in actuality is actually still going up. It's just that the cross-sectional area is going way down. So maybe this is a better way to put it. This goes way down, right? This goes down just a little bit. So overall, the stress should still be going up. Right? This should be going up. That make sense? That's a good question,
I
actually.
think it makes sense, like in relation to as strength, obviously it's not a function of strength, but is it just saying like in order to move at the same distance, taking less stress? Like,
That's for the graph, including like taking into account the cross section area, not this graph, because this one doesn't take that.
It means the following. At this point, right, if you want to get a little bit more strain, you've got to add a little bit more stress than you had before. Right? For every little bit more stress, or every little bit more strain you get, you have to add a little bit more stress. That means it's stronger. It's getting harder and stronger, right? It's called cold working, and we'll come back to it later. Whereas the plot without taking into account the instantaneous area looks like, oh, like it's getting easier and easier and easier to pull it apart. There's less force, but it's just because the area is radically reducing. Abby? Or Alicia, sorry.
So just to clarify, the engineering plots assume that the cross-sectional area stays constant the entire time, which is why it appears that the stress goes down.
Exactly right. And the reason that is because sometimes it's hard to measure the instantaneous cross-sectional area. You could, like if your experiment's running and it's going nice and slow, you could sit and watch it, watch for necking, and then get your little calipers out and start trying to measure it and hope that it's like some nice shape that's easy to measure. But because that's hard, it's just not often done. Like the right way to do it would be to account for that, because that's technically what's going on instantaneously. So let's talk about the instantaneous change real quick, right? True stress and true strain would be now, the true stress is going to be the force divided by your instantaneous area, not your initial. Sorry, I means instantaneous. The not means initial, right? True strain is written as natural log of your instantaneous length divided by your initial length. Where in the world did natural log come from, right? Where'd that come from? So strain, we knew it as your additional length over your initial length, or your additional length over initial length, right? But the change in strain would be delta sigma, right? Which is delta L over L, which means you have to take into account, you have to sum up all of your successive strain, right? So you're going to take the sum of all your changes in length over your initial length, which is another way of saying sum. In engineering, we say integral, right? We're going to integrate over it. So you're going to take dl over L, which gives you natural log of instantaneous length over initial length. And if we use the constant volume approximation, meaning whatever your area initial was and length initial was, that'll equal your area final, or instantaneous times your length final, meaning volume's conserved, then we can rewrite these expressions as follows. Meaning if you have a plot and you have engineering stress and engineering strain, which we have generally from plots, we can turn those into true stress and true strain using these two functions, right? And it'll probably be a homework question to do the proof of this, right? Are there questions? We're about out of time. Any last questions before we pick up next time? Okay, see you next time.